I'm Jules Jaffe. I'm a research oceanographer here at the Scripps Institution of Oceanography. It turned out that there was a really ideal application to building small autonomous robots that can adjust their buoyancy, migrate up and down in the water column, and that was to study plankton, the three-dimensional fields of ocean currents and how plankton get pushed around by those currents.
I'm Professor Peter Franks. I'm a biological oceanographer here at the Scripps Institution of Oceanography. One of the really interesting manifestations of physical-biological interactions in the ocean are red tides. Red tides are really dense aggregations of a particular organism that has grown to these huge concentrations. And often when you see red tides, you'll see they form stripes in the ocean that are parallel to the shore. About 20 years ago, I came up with some mathematical theories that said that if these organisms swim in a particular way, they'll interact with these huge waves inside the ocean called internal waves. I wanted to try and test this hypothesis, but to do that, you have to actually track the individual plankton in the ocean, and there's no means to do that. And so I have this wonderful colleague here, Jules Jaffe, and Jules invents instruments to look at the ocean. And he came to me and he said, well, what if we build sort of a robotic plankton? And I said, wow, that'd be great. But one plankton is not going to do what I need. I need a whole bunch of them so that I can actually test this hypothesis.
This is what we came up with ultimately. It's as we described, a grapefruit-sized autonomous robot. It has the capability of adjusting its buoyancy. When it comes to the surface, it can call us via satellite and give us its location, GPS locations, so we can go pick it up. It's got bright lights and it's got a radio frequency, kind of like your garage changer that lets us know where it is. Inside, it's got a computer. On the bottom here, we've got a buoyancy control. That means just a piston that goes in and out, and also a temperature and pressure. We want to know how deep we are. We would like to know what the temperature is around us, because that's one of the things that we measure.
So we deployed a swarm of 16 of these MAUEs in the ocean. The acoustic hydrophone allows us to get continuous localizations of these little AUEs underwater. This was the first time we've been able to test this hypothesis below the surface of the ocean, where you can't see these things, you can't track them optically. And it was fairly shocking and pleasing to find that the patterns of patch formation and dispersion of this swarm of robots looked exactly like the theory predicted. And so now I think we have a much deeper understanding of how the physics of the ocean interacts with the swimming organisms to create these kinds of patches of organisms in the ocean.
There's so many things that you can do with this. We could use them to listen to whales and dolphins, track oil spills. One of the things that came up in the Gulf of Mexico, where is the oil going? We didn't have autonomous floats. So the great thing about what I do that I love is that we can build something in a reasonable amount of time for a reasonable amount of money that will lead to really interesting discoveries about what's happening in the ocean.